Alright, this is Chapter 1, Limits and Their Properties. We're doing Section 1.2. Yes, we skipped Section 1. We're finding limits graphically and numerically. So let's talk about what a limit is. If I consider the function f of x equals x cubed minus 1 over x minus 1, where is that function undefined? Well, you'd notice that the denominator can't equal 0, so it's undefined at x equals 1. To graph this function everywhere except x equals 1, we can just use normal techniques. But how do we know what happens at x equals 1? Well, there's a few ways. To figure out what happens at x equals 1, we can find the value of the graph at values near x equals 1, approaching from both the left and the right side of the graph. So as I come in from the left, I'd try like 0.75 and get 2.313, 0.9 and get 2.710, 0.99 gives me 2.970, 0.999, getting even closer to 1, 2.997. And then I also want to come in from the right. I use 1.25, 1.1, 1.01, 1.001. Notice that from both sides, those y values get very, very, very close to 3. That's how I know what would happen. It turns out that this graph is a parabola just with a hole at the point 1, 3. Even though the graph does not exist here, we can get arbitrarily close to the point, which gives us the hole. We say the limit of f of x as x approaches 1 is 3. We write that as the limit, Lim, as x approaches 1 of f of x equals 3. Notice that the limit as x approaches 1 is stacked, kind of like a fraction, and then the f of x is big, full size, equals 3, full size also. So this just says that as x gets close to 1 from both sides, the function gets close to 3. It doesn't actually hit it, but it gets close. So what is a limit? If f becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. What's this word arbitrarily? Undetermined, not assigned a specific value. Meaning we can get as close to c as you can possibly imagine, and then get even closer. So this just means that as x gets really, 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 really close to c, the value of the function gets really, really, really close to L. So example 1, we're going to estimate the limit by evaluating the function at several points near x equals 0. I noticed that I can't just plug in x equals 0 because I would get 0 over 0. And if you've ever asked Siri, that makes Cookie Monster sad. I also know that I don't want to do these in my head. So I'm going to use my calculator. And I want to show you a little trick for the calculator. I know I'm going to plug in a bunch of values to the same function over and over. So if I go into y equals, and I enter in this function, x over, parentheses for my denominator, the square root of x plus 1 minus 1, close those parentheses. Now I don't care what the graph is, so I'm going to second quit. But now if I hit alpha and then the trace key, I get this little menu that gives me the different y's. I type that function into y1, and in parentheses, just like function notation, I'll put my x value, negative 0.01. And there's my function value. Now to get the next one, I just go alpha, y2, or y1, negative 0.001. And it gives me that value. Way easier than having to type it in every time. So if x is negative 0.01, I get 1.995. If x is negative 0.001, I get 1.9995. And let's try the next one. Oops. Negative 0.0001, get 1.99995. I can't plug in 0, so I'll just put an x through that. And we'll try these other values. 0.0001 gives me 2.00005. 0.001 gives me 2.0005. And 0.01 gives me 2.005. Now if you look at this, you'll notice that as I get closer to 0, what number do my y values get really, really close to? It seems to me like they get really, really close to 2. So I would say the limit as x approaches 0 of this whole function equals 2. And there's my answer. Our conclusion is supported by looking at the graph. This is the graph of that function, and there's a hole at the point 0, 2, but it gets really close from the left and really close from the right to the value of 2. Our next example, the limit as x approaches 2 of this function. So what is this function? Well, if I were to graph f of x equals 1, that's just a horizontal line. But that's everywhere except positive 2. And at positive 2, my function equals 0. So there's a hole in my function, and it's a horizontal line other than the hole. So coming in from the left-hand side, well, I'm approaching the value of 1. Coming in from the right-hand side, I'm approaching the value of 1, even though my graph just jumps here. So we would say the limit as x approaches 2 of this function f of x is 1. We need a limit here because the value of the function itself at 2 is not 1. F of 2 is 0. But the limit is 1 because it's approaching it from either side. It just jumps weird at that 1 point. So now, everybody's favorite Mean Girls quote, the limit does not exist. We're going to show that this limit as x approaches 0 does not exist. So we're going to pick some values from the left and from the right as we approach 0. So we'll make a little table. I would use negative 0.1, negative 0.01, negative 0.001. That should be good. 0, positive 0.001, 0.01, and 0.1. All right, again, I would just type this function in. In my calculator, I can get an absolute value. If I click Math and then go over to Num, I have ABS. So absolute value of x divided by regular x. And now I could say, alpha trace y1 of negative 0.1 is negative 1. Negative 0.01 is negative 1. Negative 0.001 is negative 1. The function doesn't exist at 0. Now if I plug in positive 0.001, I get positive 1. And positive 0.01, I get 1. And positive 0.1, I get 1. As I come in from the left, I'm approaching negative 1. As I come in from the right, I'm approaching 1. Those two ends don't meet up. So this limit does not exist. So the limit as x approaches 0 of f of x, we can write DNE for does not exist. Because f of x approaches negative 1 from the left of x equals 0 and positive 1 from the right of x equals 0. Since those two don't line up, the limit does not exist. Let's look at the limit as x approaches 0 of this one. So again, we will create a table. Negative 0.1, negative 0.01, negative 0.001, 0. Positive 0.001, positive 0.01, and positive 0.1. And I'll type these into my calculator quick. I get 100. And then I enter 0.01. Negative 0.01, sorry. I get 10,000. And negative 0.001. million. There we go. 0 doesn't exist. How about positive 0.001? I get a million. Yeah, there we go. Positive 0.01, I get 10,000. And positive 0.1, I get 100. Notice as I approach 0 from other sides, my numbers get really, 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 really big. So we would say the limit as x approaches 0 of this function is infinity. Now, infinity is a special case of does not exist. Technically, the limit does not exist because infinity is way bigger than we can conceive, but we can write the limit as x approaches 0 of f of x equals infinity because it goes up without bound. Let's find the limit as x approaches 0 of the sine of 1 over x. Notice these values I chose. They were chosen deliberately. The pi is in the denominator. So the sine of 2 over pi, that is 1. Sorry, the sine of 1 over 2 over pi. The sine of 1 over 2 over 3 pi is negative 1. The sine of 1 over 2 over 5 pi is 1. The sine of 1 over 2 over 7 pi is negative 1. The sine of 1 over 2 over 9 pi is 1. And the sine of 1 over 2 over 11 pi is negative 1. I obviously can't plug in 0, but notice that this one goes back and forth. These values are getting smaller and smaller and smaller. We're coming in only from the positive end, but that's just to highlight that it's going back and forth. Negative 1, positive 1, negative 1, positive 1, over and over and over. But these intervals that I was going are also getting smaller. These are the distance between 2 over pi and 2 over 3 pi compared to the distance between 2 over 3 pi and 2 over 5 pi. The second distance is smaller. So I'm getting closer and closer together, and it's still just oscillating back and forth. This limit, as x approaches 0, of this function does not exist because the function oscillates between negative 1 and 1 more rapidly as x approaches 0. So it becomes much more quick in its oscillation. Let me show you a picture of that graph really quick, just so you can see what I'm talking about. The sine of 1 over x, that doesn't look too bad. When I zoom trig, still doesn't look too bad. Let's zoom in. It takes its time and it goes up and down, and then all of a sudden it just doesn't know what to do in the middle there. It's oscillating forever. The closer I get to 0, it's still going back and forth and back and forth and back and forth. So that is a special does not exist limit. So there are 3 common ways that limits will fail to exist. If f of x approaches a different number from the right side of c than it approaches from the left side, if it increases or decreases without bound, that was our positive or negative infinity, or if it oscillates between 2 fixed values of x, 2 fixed values as x approaches c. And now for the formal definition of a limit. We call this the epsilon delta definition of a limit. And you won't have to do tons with this, but I need you to be familiar with it. Let epsilon, right, that's epsilon, represent a small positive number. Then the phrase f of x becomes arbitrarily close to L, means that f of x lies in the interval L minus e, or L minus epsilon to L plus epsilon. This can also be written as the absolute value of f of x minus L is less than epsilon. Similarly, the phrase x approaches c means that there exists a positive number delta such that x lies in either the interval c minus delta to c or the interval c to c plus delta. This can be written as 0 is less than the absolute value of x minus c is less than delta. This means that x can't equal c. X can never equal c, all right? And this also says that x is within a distance of delta of C. So it's at most delta away from C. If we can find a number delta and epsilon that make this true, then we can find the limit. So the definition of a limit: let f be a function defined on an open interval containing C except possibly at C, and let L be a real number. The statement, the limit as x approaches C of f of x equals L, means that for every epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus C is less than delta, then the absolute value of f of x minus L is less than epsilon. Now that's all quite tricky. So let's look at how you'll actually have to use it. Given the limit as x approaches 3 of 2x minus 5 equals 1, find delta such that the absolute value of 2x minus 5 minus 1 is less than 0.01 whenever 0 is less than absolute value of x minus 3 is less than delta. All we have to do is get this equation or inequality to look like that, except we'll have a number instead of delta. So I'm going to rewrite this inequality. I'm going to combine my like terms, so 2x minus 6 less than 0.01. And then I see there's a GCF. I'll take a 2 out. Okay, well, I can take that 2 out of my absolute value because it's positive anyway. And then divide it over. I get the absolute value of x minus 3 is less than 0.005. So that means delta is 0.005 or less. So as long as I pick a delta that's 0.005 or less, this works, and that's my limit. We mostly use this to prove a limit. To use it to prove a limit, I take those two statements. So I'll take 0 is less than the absolute value of x minus C. C is that value I'm approaching, so 2 is less than delta. And the absolute value of f of x, which in this case is 3x minus 2, minus the limit, which is 4, is less than epsilon. If I can rewrite the epsilon portion to look like the delta portion, I'm there. So I combine my like terms, get the absolute value of 3x minus 6 is less than epsilon, factor out my GCF, which is a 3, times x minus 2. Well, that 3 can be taken out of the absolute value, and then divide it over. So the absolute value of x minus 2 is less than epsilon over 3. So delta, notice that's my delta. Delta is epsilon over 3 for any epsilon chosen. And therefore, we have proved it. As long as I can find that delta, it works. All right, let's prove one more here. So I start with 0 is less than the absolute value of x minus 2 is less than delta, and the absolute value of x squared minus 4 is less than epsilon. Now this one's got a funky situation because I have to factor this. So I get x plus 2 times x minus 2 is less than epsilon. Now I can separate those out. So the absolute value of x plus 2 times the absolute value of x minus 2 is less than epsilon. I want to be left with the x minus 2. So let's think about x plus 2, the absolute value. We're looking at values that approach 2. So let's go on an interval 1 to 3, because 2 is in the middle of that. Well, between 1 and 3, the smallest this value gets is 3, and the biggest it gets is 5. So in the open interval, this value is going to be less than 5. Guaranteed, it's less than 5. All right, which means right here is also less than 5. So the absolute value of x plus 2 times the absolute value of x minus 2 is less than 5 times the absolute value of x minus 2. But that 5 times the absolute value of x minus 2 must still be less than epsilon, because this was less than epsilon. So if I divide by 5, the absolute value of x minus 2 is less than epsilon over 5. So I could make my delta equal epsilon over 5 for any epsilon chosen. And as long as I can write that equation, that relationship between delta and epsilon, I have proven it. So here's your assignment for this section.